Please at this time go onto your calendar, look for the assignment that says Exam Mod 4 Review. We're going to do this together, and I would suggest having your 3x5 note card with you and any formulas or examples you want to write down as you go. Please do that at this time. So I'm going to break this down into 2 days. So please, again, make sure that you have studied. Here you go. So our first problem here, question 1 says, the following functions model the anticipated population of various towns in terms of the number of years since 2011. Part A says, what is the population of the town in 2011? So if we look at any function, the starting value will be whatever is out in front. The base is going to indicate if there is a increase, a growth, it will be a number more than 1. It'll be a decay. It'll be a number less than 1. So if we look at this function, this is your starting population. So in this particular case, that's 7,087. Now it says, by what percentage does the population change each year as the number of years since 2011 increases? That's what the base tells us. If you write that as a percentage, that's 145%. Take off 100. If your change is still positive, in this case positive 45, that is how much it is increasing. If it is negative, that's how much it is decreasing. And then it says use function notation to represent the anticipated population of the town in 2020. So that is just how many years since 2011. That would be 9 years later. So that would just be our function h if I inputted 9. So that would be the function notation. And then what is the anticipated population of the town? Well, if I put into my function a 9, so 7,087 times 1.45 to the power of 9, when rounded to the nearest whole number, the answer I got was, because it does say round up to the nearest whole number, so that is the nearest whole number. So that's what goes here. And then we'll submit this anyway because there's lots of pieces. So that first part, part A, is now done. And now let's move on to part B. It says we have this function. What is the population of the town in 2011? Again, that's what this function represents. So that would be our starting number, 1,200. By what percent does it change? See that 1.03 is the same as 103%. So it went up by 3%. Using function notation, what would be the population in 2025? That's 14 years later. So that would be our function f, 14 years later. What is the anticipation in 2025? So if we plug in 14, we're just going to put into our calculators 1,200 times 1.03 to the 14th power. We're going to round to the nearest whole number. And so this is what my calculator reads. So the nearest whole number is 1,815. So that is B. Now let's look at C. Now, again, we have this this function g of n, n is still the number of years since 2011. The starting population is that front number, that 58,024. Now here it says, at what percentage does the population change? Now if we take that 0.85 and we write it as 85%, if we take 85% and you take away 100, we get a negative 15%. So you do have to include the negative, which indicates that the population is going down. Now, function notation says, using function notation to represent the population in 2013. Well, that is a 2-year change, so they called our function g, so that would be g of 2. What is the population at that time? If I plug 2 into my function, that's 58,024 times 0.85 to a power of 2, rounded to the nearest whole number. So we get 41922.34. Let's round to the nearest whole number. So that's 41,922 people. So that is question number 1. So there you go with that. Let's look at question number 2. It says, consider 2 job offers with salaries that are increasing exponentially. For job A, the salary for 1 year is $29,000, while the salary for year 2 will be $31,175. How many times as large is salary 2 compared to salary 1? So we're just going to take salary year 2, that 31,000 number, divided by salary year 1, that 29,000 number. And I'm not going to actually do it. I'm going to let iMath do that. So 31175 divided by 29,000. Okay. And we can see it does come out to be a nice number. Now, the salary in year 2 is what percent of the salary in year 1? So if we make this a percentage, that's 107.5%. What is the percent change? Well, just take off 100. That's your change. If it's positive, keep it positive. In this case, it went up by 7.5%. Now, for part B, it says for job B, the salary for year 1 is $27,500, while the salary for year 2 is $28,600. How many times as large is year 2 to compare to year 1? So we're going to take 28,600 divided by 27,500. I'm going to let iMath do that for me. 28,600 divided by 27,500. It does come out to be nice, so I'll hold that number for future reference. So how much did it change? 104% is that decimal value. Take off 100 is 4%. What is the percent change from year? Oh, I'm sorry. This is 104. The percent change is 4. It says you expect to keep this job for at least 5 years and you want to make as much money as possible over the time spent working. Which job should you take? Well, the first job started at 29,000. If we do that rate of change, that 1-year growth rate for 5 years, let's see how much we would make. And then we're going to do the same thing if we work on the second job, which starts here, and that goes up by that. But it's pretty clear that job A starts higher, has a higher rate of change. So we would expect that job A would be larger. And you see if you look there. So, okay. But we could figure those out if you were unsure. Let's move on to question 3. Question 3 says for the following situations, write a formula that gives the value of the investment C in terms of the number of years made, number of years since the investment was made, X. So X is the number of years since I invested. The investment started with $1,200 and increased by $58 each year. Now, that is not a percent increase. That is just an amount increase. So the formula would be C equals 1,200 plus that rate of change, that constant rate of change, times the number of years. So that is an example of a linear type change, okay? But in part B, it says it's going to increase by 1.42%, starting at $6,000. So C, in this case, would be 600 times, now we're going to add that on to 100, so 101.42% is the same as 1.0142 to a power of X. Now, part C would equal the starting value, 1,100, times our 100% decreasing by 1.19. 100 minus 1.19 is 98.81%. But in the formula, we want the decimal value to show. So let's make that 0.9881. Move that decimal 2 places back to a power of X. And then the investment starts at 1,100, decreases by that set amount per year. It's like A, except in this case, it would be subtracted per year. So that's why we have that minus. So we should have everything right there, I think. Yep. So that is how we would do question number 3. Okay. So now let's move on to question number 4. Let's make that a little wider for you so you can see it a little better if it lets me. There we go. Okay. Question number 2 says, 60 milligrams of a vaccine is given to a patient to prevent measles. The vaccine leaves the body at a rate of 5.2% per hour. To find a function that gives the mass of the vaccine remaining in the body, V, in terms of the number of hours N since the vaccine was administered. So V would equal the starting amount, 60, times, we're going to decrease by 5.2%, so 100 minus 5.2 is 94.8%. So we want to use the decimal 0.948. So 0.948. And they call the number of hours. Define a function G that gives the mass of the body. We might have to use function notation. Define a function G. Yeah. In terms of, okay, so anyway, we'll come back and change that. So a power of N. N stands for hours. So let me go and make this function notation. Whatever it's in terms of, you put in the function spot. So the function is G. We're going to call it G of N. Let's just check that's what they wanted. They want that function. Yeah, they want function notation. Okay. Now let's take a look at B. How much of the vaccine remains in the body 24 hours after it was administered? Well, we have made this beautiful equation. So we're just taking G of 24. So we're going to do 60 times 0.948 to a power of 24. I am not going to risk that iMath will accept the way I round. So I'm just going to put that in. And you'll notice the little preview looks like exactly like my formula over there. 60 times the quantity of 0.948 to a power of 24. And then it says, using your graphing calculator to determine how many hours passed before there were only 5 milligrams of the vaccine in the body. Okay, so let me close this out, and then let me open up Desmos, okay? Y equals 5. And look where it intersects, and it intersects at 46.53316. Yeah, let's see if it takes that. Yeah, okay. Finally, okay. Oh, I'm so sorry. Okay, now let's please move on to question number 5. Question number 5 says, find the value of the function when x equals 0. If you plug in 0 to this function, you just get 2.51 times 1, which is 2.51. Find the ratio of output values that correspond to increases of 1 in the input value in order to determine the 1 unit growth factor. The ratio of the output values that would be our growth rate per 1 unit, it's just going to be that 2.85, I believe. And then it says to determine the 1 unit percent change. That 2.85, if you think of it as 285%, take off 100%, it went up by 185%. The value of the function when x equals 0 is our front number 40. The growth factor is that 0.4. That's how it changes. And then the 1% change is 100% minus that growth factor. So 40% minus 100% is negative 60%. So make sure that if you subtract 100% or subtract 1, if you get a negative, that you have to put the negative. Okay, so that is question 5. Let's move on to question 6. So if we have a table here, let's go ahead and answer all the questions. The initial value is wherever the 0 is, and so our initial value in this case is 212. The 1 unit growth, we're going to take the initial value 212 divided by the first unit, so 89.04. Let me pull up some paper again so I can help you as you go through this process. So, so the 1 unit growth, we just have to take any two things that are 1 apart, whether it's the 2 and the 1 or 0 and 1. I'm going to go 0 and 1. So I'm going to do 89.04 divided by 212. And so 89.04 divided by 212 is a funky decimal. So let's let iMath just do the math for us. So 89.04 divided by 212. So that is really super close to 42%. So 100%. So 0.42 is 42% minus 100% is negative 58%. And then, oh, we don't have to put the percent symbol. What is our function? Our function, f of x, use the same variables they have used, is equal to our starting value, 212, times our 1 unit growth factor. I'm just going to put that fraction in, that 89.04 divided by 212. I'll let them deal with that, to a power of x. So let's hit submit for all of that, just to make sure everything is hunky-dory. Beautiful. So that is part A of question 6. Let's move on to part B. Now, in part B, the initial value, I'm going to find the 1 unit growth factor, and then since I am 1 above that, then I have to go backwards one. Okay, so let's do part 2 first. So things that are 1 unit apart are 316179 and 24.51 are 1 unit apart. You always put one further on top and then one underneath, the one before it underneath. So 31.6179 divided by 24.51. I'm just going to type that in because, well, you know. Let them do the math. Okay. Now, if you look at the preview, that looks like 1.29 or 129%. So if we take off 100, it's 29%. So the percent change is 29%, which is in the positive. Okay. What is our function? Well, not yet. I need to know the initial value. So if I was one ahead, that 24.51 is the first one. I need the 0 value. So I need to divide off the growth factor. So I'm going to divide by 1.29. So 24.51 divided by 1.29 is 19. So my starting value, now I know, is 19. So what's my function? So they called this one g of x, so we're going to call it g of x, equals 19 times 1.29, or that fraction again, to a power of x. Unless I type something funky, there we go. So that is question 6. Let's move on to question 7. If I could hit question 7, there we go. I'm doing good today. I'm doing good, really. I'm okay. So let's look at question 7. It says the value of a car depreciates each year. Suppose that your car, you purchased a car for $23,500 and the value of the car depreciates by 11% each year. Determine the initial value of the car. That's the $23,500. The 1-year growth factor. Now let's think about the fact that the growth factor, you have to start with 100, and if it's depreciating, you're going to subtract off that percentage. If you're growing, you're going to add it on. So 100 minus 11 is 89, so that would be 0.89. So the 1-year percentage change is 0.0, or I'm sorry. We're going to subtract that from 100. That's where the 11 comes in. It went down by 11. Let's make sure to make that a negative. To find a function that determines the value of car in terms of the number of years, they called it f. See, they're the function f. So let's make it f of x equals our starting value, 23,500, times our 1-year growth factor, 0.89, to a power of x. Let's kind of check everything right now to make sure we're okay. And then it says determine the value of the car in 8 years. Well, we've got this beautiful function. So let's plug in 8, which would be 23,500 times 0.89 to the power of 8. Okay. Now I'm going to let iMath do a little math, and then I'll write down what they say, and then we'll round it to the nearest penny. So 0.89 to a power of 8. Okay. So for money purposes, that's $9,250.98. So I'll erase it, and I'll put in 9,250.98. And there you go. So there's question number 7. Let's look at question number 8. Now, question number 8 is comparing a linear function versus an exponential. Okay. So a linear function, let's take a look at what we know. It's kind of like we have to find the slope and the y-intercept, the starting value. So we know the starting value for both of these, we'll call it our P, is 8,800. Okay, now, oh, I'm sorry, it's not. In 2012, the starting value is 13,000. Now, for a linear function, you want to think of slope, the change in y over the change in x. So our y values are the amount, the x values are the years. So we went up by 2 years, and our price went down by whatever 88. Let me erase that. Whatever 8,800 minus 13,000 would be. So 8,800 minus 13,000 is, it went down by 4,200 in 2 years, or 2,100 per year. So for a linear equation, our f of t would be our starting value, 13,000, minus our change per year. So it went down by $2,100 each year. So then it's just a times that number of years. But our exponential function, we need a percent change. We need a growth factor per year. So if we think about the fact that they called this one G. So our G of t would be our starting. Now, it is our ending value, 8,800, over our starting value, 13,000, to a power, but we have to divide it by 2 because it was a 2-year change. And I'm going to let iMath do all of this work. And then it looks like what I want it to look like. I forgot to put in the G of t. So always look at that preview. It's going to yell at you and say if it is what you want it to be or whatever. So you'll notice one of these equations is linear and one of these equations is exponential. Let's move on to question 9. So what is the 1 unit growth factor? That's going to be that 0.08, or 0.8, I'm sorry. The 2 unit growth factor, we would just have to square that. So I would put 0.8 squared. The 8 unit factor, 0.8 to the 8th. Oh, I didn't put a 0 there, did I? Let's check that they're okay with those. And then this last one, a third. If we know the 1 unit growth factor, we're just going to take that 0.8 to a power of 1/3. Put that 1/3 in parentheses. And same thing here, 0.8 to a power of 1/4.